So this is the video on the chapter 8, Introduction to Trigonometry. So in the previous video we saw what is trigonometry and what are the basic six trigonometric ratios that exist with respect to a triangle. Now we continue our discussion with respect to this trigonometric triangle, and we want to see two important properties with respect to this branch of or this topic of trigonometry. Okay, so trigonometric ratios rather have two important properties. The first one, which we're going to see right away. So consider this right angle triangle. Consider this right angle triangle. This is our right angle. Okay, and I'm going to name these sides. This is A, this is B, and this is C. Okay, let's give the value of lengths to each of the side. Let's consider this as standard right angle triangle, 3, 4, and this will be 5. Okay, now in trigonometric ratios the focus is always on the angle. Okay, sorry, the focus is always on the angle. So you have to choose an angle before we start discussing trigonometric ratios. So here we choose angle A. So let's consider this angle A, and let's assume this angle A has some value. Let's say randomly, let's say this is 32 degrees. Okay, so this angle A, this CAB, this angle is of 32 degree. Okay, now okay, now let's come back here to what is the definition of sine of A. So sine of A is defined as side, okay, side opposite to A or to angle A, the whole divided by hypotenuse. Okay, this whole divided by hypotenuse. This is the standard definition of sine of A. So in this case, this is going to be equal to side opposite to angle A. What is the side opposite to angle A? It's BC. So I'm going to write it here. BC divided by what is hypotenuse? Hypotenuse is the side opposite to the right angle triangle. So it's going to be AC. So BC divided by AC, which is in fact equal to, this is 4 and AC is 5. So 4 divided by 5 is equal to 0.8. So 0.8 is the value of sine of angle A, and this angle A is of 32 degree. It's an assumption. Don't get very worried about why this 32 degree came. Whatever, even 32, 35 doesn't matter. But this is the value of sine of A for this particular angle. Sorry, for this particular triangle. Now I'm going to do some additional construction on this triangle. So first I need to create a copy of this. So let's come down here and paste. Okay, so let's move it here. Okay, now I'm going to do some additional construction on this triangle. What I'm going to do is I'm going to extend this hypotenuse and this base to create another right angle triangle, a bigger right angle triangle. So it's going to be something like this. So let's extend it. Okay, and then from here I'll come down till here, and I'll just extend this as well. Okay, so obviously this is our right angle triangle, and yeah, okay, that's all. So this angle, or rather this triangle ACB, has been extended and we have got a bigger triangle now. Okay, let's give some name to that bigger triangle. So I'm going to call it Q, and let's call this P. Okay, so we have two triangles now. Let me write it down. We have triangle AQP, and we have the original small triangle, which is ABC. In fact, let's name it properly. Okay, since we are naming this since we are naming this ABC, I will name it APQ. So triangle APQ. Okay, now we all know that these two triangles APQ and ABC, they are similar triangles. Okay, they are similar triangles by the property of angle. So angle A is common to both these triangles, and this 90-degree right angle triangle is also common to both these triangles. So thus triangle APQ is similar to triangle ABC. Okay, and now property of similar triangle is that the ratio of the sides are also equal. Okay, so what I'm going to write here now is important ratio that yes, okay, so BC divided by AC, okay, is equal to PQ divided by AQ. Okay, so I'm just going to write here the property. This is by property of similar triangles. This is the property of similar triangles. Their sides are in proportion. Okay, so let's quickly see. So BC by AC is equal to PQ. So PQ and BC. So PQ and BC and AQ and AC. So AQ and AC. So this ratio is going to be equal to. This ratio is going to be equal because these two triangles are similar. Now focus on this big triangle APQ. Okay, for APQ, I'm again going to be writing sine of angle A. Okay, now sine of angle A is also again equal to opposite side. Okay, opposite side divided by hypotenuse. This is our standard definition of the trigonometric ratio sine of A. That is equal to what is the opposite side for angle A? It is equal to PQ. So I'm going to write here PQ. And what is the hypotenuse of this big triangle? The hypotenuse is AQ. So that is equal to AQ. However, PQ by AQ is equal to BC by AC. Okay. So I'm going to write here this is equal to BC by AC. However, as seen above, we already have the value of BC by AC. BC by AC is 0.8. So I'm going to write here BC by AC is equal to 0.8. Thus, we observe that if the length of the sides of a triangle change, but the angle remains constant. So the angle was 32 degree here and the angle is 32 degree here. If the angle is remaining constant, okay, and the length of the sides of the triangle are increasing or rather changing, the value of sine A remains the same because the angle remains the same. Okay, which means thus an important property that the value of angle A determines the sine of A. Okay, not the value of the sides of the triangle. It's the value of the angle that is more important. If this is 32 degree, this is 32 degree, then the value of sine A is going to be same. The same goes for all the other trigonometric ratios. Okay, whether you take cos of A, tan of A, cosec, sec, or cotan of A, the property that if the angle is same, then the value is also going to be same is holds. The property also holds. So that is an important point which I have noted down here. Let's zoom in. Okay. Now, hold a minute. Let's erase this angle. Yes. Okay. So this is the property which we wanted to highlight when it comes to trigonometric ratios. Let's read it. If the angle remains the same, then the values of the trigonometric ratios do not change with the lengths of sides of triangle. Okay, so it doesn't matter what is the length of the sides of the triangle, or whether it's a small triangle or this big triangle, or if you draw another big triangle, does not matter. The value of the trigonometric ratios, okay, very important, trigonometric ratios, so that includes all the trigonometric ratios. So these trigonometric ratios include all the 6 trigonometric ratios, which is sine and cos and tan and sec and cosec and cot. All all these 6 trigonometric ratios, they do not change with the length of sides of triangle. We just took the example of sine of A to get to come to this conclusion of this. But even if you start with cos of A for the same triangle, or even if you start with sec of A for the same triangle and go ahead, you will observe that if the angle remains the same, then the value of the trigonometric ratios, these are my trigonometric ratios, do not change with the length of the sides of triangle. So this is an important property of trigonometric ratio. Okay, this is the first property that we wanted to discuss in this video, and now we come to the second property with respect to trigonometric ratios. And for the second property, again I'm going to need this triangle. Just create a copy. Okay. All right, create a copy, yes, and let's paste it here. Paste. Okay. Okay. Now, so this is again a triangle that we have, and let's focus on angle A. Okay, the value does not matter. 3, 4, and 5. Now let's take sine of A. So as we saw, sine of A is equal to the opposite side. I'm going to write it again for the sake of emphasis. Opposite side upon the hypotenuse. Okay, and cos of A is equal to adjacent side upon hypotenuse. So these are our standard definitions of sine of A and cos of A, which are both foundational trigonometric ratios. Now, if you note that in any right angle triangle, the hypotenuse is always the largest side. Okay, let me zoom in and make this point very emphatic. The hypotenuse, this hypotenuse is always the largest side in any right angle triangle. Okay, the same goes for this as well. This. Okay, so the hypotenuse in any right angle triangle is always the largest side of the triangle. Thus, if this is the largest side of the triangle, then any other side divided by this largest side is always going to be less than 1. This value or this ratio is always going to be less than, or in some very rare cases it will be equal to 1, but in general it will be less than 1. Why? Because this denominator is always going to be greater than the numerator. And why the denominator is going to be greater than the numerator? Because this denominator, which is the hypotenuse, is always the largest side in any right angle triangle. Even in this triangle ABC, you can see AC, which is the hypotenuse, is the largest side. And what is the hypotenuse? Hypotenuse is the side opposite to the right angle. Okay, so this is the another property that we wanted to focus on. I made a note here. Okay, the sine and cosine of the angles will always be less than or equal to 1. Okay, in very rare cases it will be equal to 1, otherwise mostly they will be less than 1. As we saw here, sine of A was less than 1, 0.8. Similarly, if you see cosine of A, in fact, let's make a note here. Okay, if you zoom in and let's find cosine of A. So cosine of A will be equal to 3 divided by 5. That will be equal to 0.6, which is also less than 1. So both sine of A and cosine of A in any triangle is going to be less than or equal to 1. This is the second property that we wanted to discuss with respect to trigonometric ratios. So these are the two properties. These two properties are very important when it comes to trigonometric ratios.